Okay, so today I'm going to approximate the value of pi using geometry and trigonometry. There are some formulas that I'm going to assume you all are familiar with. The area of a circle, pi r squared; area of a triangle, 1/2 base times height; SOHCAHTOA, sine, cosine, tangent; and law of sines. So to approximate pi, first we're going to start off with a circle with radius 1, as shown here. We use 1 so that our radius is 1 and 1 squared just equals 1, so our area is just pi, which is really useful because we're approximating pi. So the circle is going to have a polygon of n sides inscribed inside of it. So over here you can clearly see it's a hexagon, but for the purpose of this explanation, we're going to say that it has n sides. So over here, this angle, I'm going to call it the central angle because it's connected to the center of the circle. This central angle for this specific triangle is going to be 360 divided by n degrees. So we know it's going to be 360 divided by n because if we drew a smaller circle here, that circle would have 360 degrees. We divide it by n number of sides, so in this case, let's say we have a hexagon as shown. We have 6 sides, so we're going to divide 360 into 6 equal parts. So this n value over here, this central angle for our triangle, would have a value of 60. If we had a triangle inscribed in it, then we would divide 360 by 3 sides, and our central angle would be 120 degrees. But for now, it's 360 over n, and we're going to take this specific triangle, the one marked x, and we're going to bring it out here to get a closer look at it. So there's our triangle. These sides are equal to 1, and that is our central angle up here, 360 over n. Now to find the area of this triangle, we need to use our formula 1/2 base times height. So we need a height. So we're going to drop an altitude straight through the middle, perpendicular to the base, so we have 90 degrees over there. We want to get right triangles as much as possible because they're really easy to work with. They are our friends. And you can see that the altitude cuts this central angle in half. So we have 360 over 2n, or more simply, just 180 over n degrees. Now, we want to get the height, and we can do this using trigonometric functions. This length over here is adjacent to our angle, and our hypotenuse is 1. So we can use adjacent and hypotenuse and use cosine. So the height of this is equivalent to the cosine of 180 over n. We can say that because it's not being divided by a value besides 1. 1 doesn't change the value of this, so we can say that it's just cosine of 180 over n. Now, this segment here is exactly half of the overall base, which is exactly what we want. So we're going to say that this segment over here is the opposite of this angle, and we have the hypotenuse, so we're going to use sine. So the length of that segment would be sine of 180 over n. Now to find the area of this overall triangle, we're going to see that we have the height times half the base. So this little part here is the area of the overall triangle that we have zoomed out. But we have to remember that we're actually looking for the area of the entire polygon of n sides. So if we have a hexagon then with 6 sides, we'd have to multiply this by 6, because we have 6 triangles around here. So if we have n sides, we'd have to multiply by n triangles around. So this all has to be multiplied by n. And that would be the formula for the area if you're looking at an n-sided polygon within a circle of radius 1. Let's move, I'm going to erase this. Let's move to the area of a n-sided polygon outside of a circle with radius 1. So we can see here, again, it looks pretty similar to the diagram above, except the polygon is now outside of the circle. So once again, we're going to take this triangle over here that I've drawn in, we're going to zoom it out, make it big, get a real close look at it. And this time we have to, our hypotenuse, we have to keep in mind, is not equal to 1. So this length over here, does not equal 1. Instead, our height down the middle is equal to 1, because that's our radius of the circle, from center down to the end. So our height is equal to 1. Make a right triangle, because they're really friendly. And our angles don't change. This central angle of the overall triangle is still 360 over n. Divided by 2, you still get 180 over n. But now our height is already given, so we don't have to worry about this. And now we're just looking for the base. Again, it's just half the base, so we can use, we don't have the hypotenuse, so we can't use sine or cosine. So what do we use left? We have tangent, because we have our adjacent, and we're looking for our opposite. So we have opposite over adjacent, which is just opposite over 1, which is just equal to opposite. So we can see that this value, this length, our half base, is equal to tangent of 180 over n. So, and that we're actually done. So the area of that triangle is equal to tangent of 180 over n. But we're not actually done, because we have to keep in mind that this is just a smaller segment of the overall polygon, and have to multiply it by n sides. So that's what it would be if the polygon was outside of the circle, with the circle of radius 1 inscribed. And there's actually a really interesting trend. I'm just going to erase what we have here. For a polygon inscribed within a circle, so what we did the first round, as the number of sides increase, the area becomes bigger. The area of the circle stays at a constant pi, as we showed here, but the inner polygon fills up the space, as you can see here. If you had a triangle inside, it doesn't fill up a lot of space because you still have these areas out here. But if you had, let's say, a hexagon, because I really like hexagons, if you had a hexagon, you can see that these areas that aren't filled up, they add up to a lot less than these areas. So as the number of sides increases, it starts to look more like a circle and starts to take up enough space as it approaches the area of a circle. For a circle inscribed inside a polygon, so we have a circle with a polygon around it, so let's say a hexagon. As the number of sides of the polygon increases, the area actually becomes smaller as it fits to close around this inner circle, which stays at area pi. So when the number of sides increases, again, it becomes more like a circle. It approaches circular shape, and it sort of shrinks in, if you can visualize this sort of shrinking into the size of a circle. So that's a good trend to keep in mind when sort of thinking about how to approximate pi and using geometry and trigonometry to figure that out. With problems like this, it's good to have a good technique and a good way to approach the problem. So some techniques that I use is basically writing down all the formulas that I think would be useful. So I thought that would be useful because we involve circles. I thought the area of a triangle would be useful because we're dividing these polygons into smaller triangles. SOHCAHTOA is extremely useful because we're using trigonometry to approximate pi, and it actually turns out we didn't use law of sines, so I thought that would come in handy, but in fact it didn't. We didn't even need it. And that's alright. It's good to be a bit over-prepared, I guess. Another thing also, instead of going for the full Monty, I guess, and just trying to calculate the area all by itself, it's easier to look at it and think, this can be broken up into smaller triangles, because it's really easy to calculate the area of a triangle than to just try and figure out the entire area off the bat. And even more important than that, I guess, would be using common sense and logic to sort of proofread and like check your answers at the end. Because when I was calculating the area of a polygon around a circle, I was actually doing a hexagon, and I got that the area of the larger hexagon would equal 3. And that makes absolutely no sense, because the area of the circle is pi, and since the hexagon was greater than the circle, how can the area be 3? Because pi is greater than 3. So it's good to think about it's good to constantly think about what you're actually doing and checking your answers at the end, because it does make a big difference. If I left it as 3, my data and my conclusions would be extremely off. So it's really good to sort of keep this in mind and have sort of a fail-safe and like always check your answers. So for our final conclusion, I guess, we could say that the area of an n-sided polygon within a circle, so inside a circle, is area is equal to sine of 180 over n, which is our half base of our small triangle, times cosine 180 over n, which is our height down the middle, times n, of course, because we can't forget about the number of actual triangles we have. And the area for a polygon where the circle is actually inside it, so the circle is inside the n-sided polygon, our area would just be tangent of 180 over n, which is our half base, and our height's just 1, so we have our imaginary friendly 1 over there, which we actually don't even need to include, so I'm not going to. And then this is just our smaller triangle, and we need to multiply it by the number of triangles that we have. So, there you have it. Approximation of pi. As the number of sides increases, the closer you get to the value of pi. And that's it.